All right, let's do trigonometric integral, section 3.2. These are going to be some trig identities that will be useful in this section. I would argue all of them are the most important, but you don't necessarily need any other ones besides these 8. I think these 8 are going to be sufficient for the rest of this section. So just kind of make note of those, keep those maybe in front of you while we're working through some of these, and we're going to just practice more techniques for integration. So first example, the integral of cosine squared. Well, I don't know the antiderivative of cosine squared off the top of my head. I could write it as cosine times cosine and then try to do an integration by parts. I encourage you to try it. It won't end up working very nicely. So the real way to do this is to use this trig identity that we have here, which is cosine squared of x is 1 plus cosine of 2x all over 2. So this integral then becomes the integral of 1 plus cosine of 2x divided by 2 dx. And then there's a couple of ways you could do this. You could take that 2 outside the integral and make it a 1/2 outside the integral. That would be fine. Or you could break up the fraction and turn that into the integral of 1/2 plus 1/2 cosine of 2x dx. And then you can do the antiderivative of each one of those. So 1/2 x plus, then this 1/2 is a constant multiple. The antiderivative of cosine is sine, but of course divided by the constant multiple. So this is 1/2 x plus 1/4 sine of 2x plus c. Ta-da! Okay, so not particularly challenging in any way, but just as a good reminder that trig identities are going to be very useful for finding antiderivatives. Another one. What about if it weren't squared? What if it were to the power 4, for example? This one's a little bit trickier, but I'll walk you through it. This first step would be to break it up to be sine squared times sine squared. And then I could use those trig identities. So this would become the integral of 1 minus cosine of 2x over 2 times, and then the other sine squared is also 1 minus cosine of 2x all over 2 dx. And now I'm going to do this. That 2 times 2 on the bottom is a 4. So I'll take the 1/4 outside the integral. And then I've done that. I now have 1 minus cosine of 2x times 1 minus cosine of 2x, which you would FOIL to simplify. Okay, so it really does come down to simplifying. So 1 minus cosine of 2x minus a cosine squared of 2x dx. Maybe make a note to yourself that that was through FOIL. Okay, and then I'm going to continue on. The antiderivative of 1 is good. I know that one. The antiderivative of cosine is good. I also know that one. The antiderivative of cosine squared, I don't know. I have to do the trig identity again. So this is going to become 1/4 the integral of 1 minus 2 cosine of 2x plus the trig identity for cosine squared is 1 plus cosine of double the angle over 2 dx. I'm going to write that down over here to the side because cosine squared of theta is 1 plus cosine of 2 theta divided by 2. So if there was a 2x on the argument of that cosine squared, it became a 4x in the argument of that cosine. And then I can simplify from there. So this will become 1/4 the integral of 1 minus 2 cosine of 2x plus 1/2 plus 1/2 cosine of 4x, and then you do the antiderivative from there. So 1/4 times x minus 2, the antiderivative of cosine is sine. Don't forget to divide by the constant multiple, 1/2 x plus 1/2 sine of 4x divided by 4 plus c, of course, in this case. I'm going to give you guys a second to catch up. I know that's kind of a lot, but obviously feel free to pause at any points. I'm just going to simplify and give myself some space so I can write out that final answer there. So then this became 1/4 x minus 1/4 sine of 2x plus 1/8 x plus 1 over 32 sine of 4x plus c. Ta-da. Ta-da. Okay. Let's do some more. What about cosine cubed? Another trick is sometimes that half angle or double angle identity doesn't help us. Here's an example. If that were cosine to the power of 4, I could do what I just did for the previous example. If it were cosine squared, I could also do what I just did for the first example. But if it's a cosine or a sine to the power of an odd number, you have to first break up the original integrand to be the integral of, this will now become a cosine squared of 4x times a cosine of 4x. All right, so a little bit different there, I think, right? That's definitely a little bit different. Dx, of course. Now that you have that, then I want to think about another way to do this. I know that sine squared plus cosine squared is 1. So sine squared of theta plus cosine squared of theta equals 1. That tells me that cosine squared is 1 minus sine squared. The reason why I used this trig identity rather than the half angle identity is because now the arguments of all the trig functions are the same. You always want the arguments of the trig functions to be the same. Then you can do a really standard u sub. So I'm going to let my u be sine of 4x. The derivative of sine is cosine multiplied by the derivative of the inside. So du divided by 4 is cosine of 4x dx. So this becomes the integral of 1 minus u squared times du divided by 4. Much easier, 1/4 u minus u cubed over 3. And then I know what my u is. So 1/4 times sine of 4x minus 1/12 times sine cubed of 4x. I distributed that 1/4 across. That's where that came from. I was just distributing that across. Ta-da! All right, let's do another one. So that's using the Pythagorean identity when you have sine or cosine to the power of an odd number. You should use the half angle formulas or identities when you have sine or cosine to the power of an even number. And then what about if they're both to the power of an even, then I should use those half angle identities. So if they're both to the power of an even, you should turn that into 1 minus cosine of 2x over 2 times 1, there we go, 1 plus cosine of 2x divided by 2. That's the trig identity for sine squared and cosine squared each. Then I can take that 1/4 outside the integral, and then I could FOIL. I'll skip the FOILing for you, but it is 1 minus cosine squared of 2x dx. And then again, I don't know the integral of cosine squared, so I would use that same trig identity. Don't forget to double the argument. So 1 plus cosine of 4x over 2, and then don't forget to distribute. So 1/4, 1 minus a half minus 1/2 cosine of 4x dx, because technically there was a set of parentheses here and that minus would need to distribute. Okay, yeah, that's a little trickier, I suppose, right? And then we would have to simplify from there. Was there other ways to do this? Yeah, totally. There's definitely other ways to do this. But now I could, by the way, I know I'm not done with that problem. You could just do the antiderivative from there and you'll be fine. I just want to point out that there was another thing that you could have noticed. So I could have noticed something a little bit different. So I'm going to kind of bring those two steps off to the side and sort of ignore them for now. I could have noticed that this is 1 minus cosine squared, which I know from the Pythagorean identities is sine squared of 2x. And then I could have done the trig identity for sine squared, which is 1 minus cosine of double the argument over 2 dx. I thought that was a little bit smoother for me anyways. So 1/8 times the antiderivative of 1 is x. The antiderivative of cosine is sine. Don't forget your plus c. Ta-da. Okay, let's do another one. Let's do another one. It's just a bunch of practice. You're just using the trig identities. 3.2 is using those 8 trig identities over and over and over again. So have them in front of you while you're working on your homework, and then try to practice with the quizzes and any other types of practice you want to do. Try to practice without having those trig identities in front of you. Make sure that you can come up with them on your own. Let's do the same thing for this one. I'm going to break this up one more time. This will become the integral of sine of x times sine squared of x times cosine to the 3/2 of x dx, which will turn into, using the Pythagorean identities, sine squared is 1 minus cosine squared. And I used the Pythagorean identities, not the half angle identity here, because I wanted all of the arguments to stay the same. And then I'm going to do a u sub. So once I do that, then I can do my u sub. I'm going to let my u be just cosine, and then du would take care of that extra sine of x dx. So I'll highlight that. That entire sine of x dx is now du. So this integral becomes 1 minus u squared in parentheses times cosine to the power of 3/2, which just turns into a u to the power of 3/2. Then it's a way easier. Then I can do the algebra, distribute across. This will become the integral of u to the power of 3/2 minus u squared times u to the 3/2. And you know properties of exponents. I could add those two exponents. And if I add those, it would be 2 plus 3/2, which does become the power of 7/2. Cool. Yeah, all right, so then I can integrate. So then this will become add 1 to the power, so u to the 5/2 divided by 5/2 minus u to the 9/2 divided by 9/2 plus c, and then I replace my u. So 2/5, I can't remember what my u is. It looks like it was cosine. So 2/5 times cosine to the 5/2 of x minus 2/9 times cosine to the 9/2 of x plus c. Ta-da! All right, same kind of idea for the next one. I'm going to set it up. I'm not going to finish solving this one, so you'll want to set it up with me, and then you'll want to pause the video and see if you can finish it off on your own. But let me set it up for you. This will become the integral of cosine to the, let's do this, cosine squared of x squared times an extra cosine times the sine of x to the power of -2. I think if you write the power of -2 like this, it might make the u sub more obvious. I'm not saying you have to, I'm just giving you a tip. And I'm going to set it up a little bit farther. This will become the integral of 1 minus sine squared. I'm using the Pythagorean trig identity here, times cosine of x times sine of x to the -2 dx. You're going to want your u to be sine of x and see what you end up with. This one's a little bit harder. If you ended up with that u being sine of x, some of this is going to be a little bit trickier. You're going to have to do lots of foiling along the way. So pause the video, try it on your own. Okay, maybe now you're back. Here's what I got as the answer. -1 over sine of x minus 2 times sine of x plus sine cubed of x over 3 plus c. If you didn't pause to try it on your own, now's your time. Pause and try it on your own. Make sure you can do it. Okay, let's do another one. All right, now we're going to do the integrals of all 6 trig functions. This is another big part of section 3.2 of our trigonometric integral. So we have to do all of them. All right, and what's tricky here is that some of them we already know. And then the ones we don't know become real tricky. So let me walk you through it. So the integral of sine of x dx, we already know. It's negative cosine of x plus c. Done. Okay, what about the integral of cosine of x dx? Yeah, we already know that one. It's sine of x plus c. Done. Check. All right, let's keep going. What about the integral of tangent? So the integral of tangent of x dx, that one's harder. Not too much harder though. So I'll walk you through it. I would rewrite that as the integral of sine of x over cosine of x dx. Then I could do a u sub, let u be cosine, and its derivative will take care of that extra sign, although I have an extra negative. So this will become the integral of -1 over u du, which of course becomes negative ln of u plus c. So then I really have the answer to the antiderivative of tangent is negative ln of cosine of x plus c, which is good. That's correct. That is totally correct. And if you want to memorize it that way, that's correct. For some reason, a lot of times mathematicians like to write things super simple and kind of narrow it down to have the less to write down is more. This negative could come up as an exponent, and cosine to the power of -1 is 1 over cosine, and 1 over cosine is secant. So you're going to often see people having it written as ln of secant. I would accept either. Those two are both correct. Whichever one you want to memorize. I recommend you just pick one to memorize. Or maybe you memorize none of them and you just do a use of every time. That's also totally fine. Okay, and then if you're willing to trust me, or pause the video and try on your own for cotangent. Rewrite it as cosine over sine, try a use of. You're going to end up with ln of sine of x. That one didn't have an extra negative. Okay, we have just a couple of more. We already found 4 of them. That's great. Just a couple of more. I'm going to do this next one in a different color because it's quite tricky. So the integral of secant. This one is much harder, but it's really, really important. It's going to show up a lot. So this one you really, really do. You're going to probably end up memorizing it because you're going to see it so many times. This one's kind of tricky. I really like this one because it's super interesting that somebody, I don't know who, I don't know who in mathematical history. Somebody spent a lot of time playing around with this and trying all kinds of things until they found something that works. And we are kind of lucky now to live in a day and age where we just know that somebody already figured it out. And so here's what's a cool thing that worked. So what somebody did is they tried multiplying this top and bottom of the fraction by a million different things. And it's so amazing to me that somebody then figured it out. Let me multiply this top and bottom by secant of x plus tangent of x. I'm always allowed to do that because all I did was multiply by 1. And then let's simplify that. If I simplified that, this would become the integral of my denominator is now secant of x plus tangent of x dx. And the numerator I'm going to distribute across. If I distribute across, that's going to become a secant squared of x plus a secant of x times a tangent of x. And then I can do a nice use of, let my u be that entire denominator, secant plus tangent. Then du, the derivative of secant, is secant of x, tangent of x, plus the derivative of tangent is secant squared of x. And then I'm going to highlight it because I think it's just really awesome. That whole thing, like if you think about this, let me highlight it even more clear actually. Secant of x, tangent of x plus secant squared times dx is the entire numerator. That's just really cool. Like that just happened to match so nicely. I think that's really awesome. So then that becomes the integral of just 1 over u du, which of course we know is ln of u, and my u was secant of x plus tangent of x plus c. So now I know that the integral or antiderivative of secant of x is ln of secant of x plus tangent of x. And then I'm going to do something else. I'm going to write down the next one. Same idea for cosecant of x. I'm going to write down the answer, but I strongly encourage you to pause the video and try to come up with it on your own. See if you can come up with it on your own. It ended up being negative ln of cosecant of x plus cotangent of x plus c. All right, so now we have the antiderivatives of all 6 trig functions. The sine and cosines we already knew. I think those were easier ones. It's the tangent, cotangent, secant, and cosecant that are a bit new to us. But that's going to be something we're going to use a lot. So maybe we should write those down as a quick summary. And actually, I think I'm going to do that for this video. Let's write them all down as a quick summary. So I know the integral. You should write these down as well because you're going to need to know them. The integral of sine of x is negative cosine of x. The integral of cosine of x is positive sine of x. The integral of tangent of x is ln of secant of x plus c. The integral of cotangent of x is equal to negative. No, that one did not have a negative. Of course, I'm so sorry. It's positive ln of sine of x plus c. The integral of secant of x dx is equal to ln of secant of x plus tangent of x, and then the integral of cosecant of x is equal to negative ln of cosecant of x plus cotangent of x plus c. So here is our nice little summary of the antiderivatives of all 6 trig functions. Cool. Let's practice. Let's practice. So here's an example. The integral of 3x squared times secant of x cubed dx. You might be tempted to try integration by parts. You might be tempted to try integration by parts because you see a product. I don't blame you. However, you need to first try U sub. And if that doesn't work, then you think about integration by parts. And in this case, U sub should be the obvious one because I have an inside and its derivative is right there on the outside. So this is really just a chain rule backwards. So I'm going to let my U be x cubed. Du is 3x squared dx, which matches perfectly. So this becomes the integral of secant of u du, which we just figured out, is ln of secant of u plus tangent of u plus c, and of course replace. So ln of secant of x cubed plus tangent of x cubed plus c. Ta-da! Let's practice another one. So the integral of secant of 3x, don't forget to divide by constant multiples when the inside is linear, just like we've been doing in Unit 1 a whole lot as well. So the integral of secant is ln of secant plus tangent. You keep the arguments the same. You just divide by the constant multiple minus the antiderivative of cotangent was ln of sine. You keep the argument the same. You just divide by that constant multiple. Let's see. Ta-da. All right. We're doing really good. So now we're going to get to some that are maybe slightly trickier, only because you probably don't think about the tangent and secant trig identities very often, but we really should. So now's a good time for us to remember the tangent and secant trig identities that are part of those 8 that you saw at the beginning of this section. One of the Pythagorean identities is sine squared of theta plus cosine squared of theta equals 1. And if I were to take that single Pythagorean identity and divide both sides of the equal sign by cosine squared of theta, then I would get sine over cosine, which is tangent, plus cosine over cosine is 1 equals 1 over cosine is secant. So then you end up with the other Pythagorean trig identity. So that's going to be a really useful one for us. Maybe we don't write that one down as often as the sine squared plus cosine squared, but we really should start writing it down just as often. It's going to show up a lot. So let's do this integral. Tangent cubed times secant to the 4th. What I'm going to do is rewrite that as tangent cubed of theta times secant, I said theta, I'm sorry, I guess the letter here was x, but it doesn't matter. Secant squared of x times secant squared of x dx. And then I'm going to rewrite this as the integral of tangent cubed of x. I'm going to take that first secant squared and I'm going to turn it into tangent squared of x plus 1. And that second secant squared, I'm going to leave alone. So I'll highlight that so you can see it. This secant squared, I used that trig identity for. Everything else I left alone because the goal was to try to manipulate this until I can do a simple U sub, just like we were doing in the previous examples. So if I were to let my U be just tangent, just the tangent, then its derivative is going to take care of that extra secant squared because the derivative of tangent is secant squared. So then this integral becomes the integral of, instead of tangent cubed, it's now U cubed. Instead of tangent squared, it's U squared plus 1 and then du. And then this is something that I can integrate as well. I'm going to turn that into the integral of u to the 5th plus u cubed. I distributed. Then I'll do the antiderivative as 1/6 u to the 6th plus 1/4 u to the 4th plus c, and then last but not least, replace. So 1/6 tangent to the 6th of x plus 1/4 tangent to the 4th of x plus c. Ta-da! All right, kind of tricky, kind of tricky. Let's do another one. Let's do another one. So for this one, I'm going to write down the other Pythagorean identity, which was 1 plus cotangent squared of theta is cosecant squared of theta. Again, this is one we probably don't write down very often, but I know you learned it in a trig class. Definitely write it down now and maybe more often to help you remember it. So that's what I've got there. And then I'm going to do this integral of cosecant cubed times cotangent cubed. A little bit tricky, but I know we can do it. This is going to turn into the integral of cosecant squared of x times, there's more than one way to do all of these problems, by the way, so you might come up with another way, but just so long as you're using the trig identities correctly, you'll be fine. Cotangent squared of x times cotangent of x dx, and then I'm going to take one of these trig identities here. I'm going to look at that cotangent. I'm going to be kind of careful about this one. I'm going to take that cotangent squared and use that trig identity. This will become the integral of cosecant squared of x times cosecant of x times cosecant squared of x minus 1 times cotangent of x dx. I'll highlight that there because I brought that 1 to the other side of that equal sign to get cotangent squared by itself. And then I'm going to do a u sub. This is another u sub that maybe we're not super familiar with, but it's a good one to get extra practice with. If I were to let my u be just cosecant, remember the derivative of cosecant is negative cosecant times cotangent. And so that means that the du took care of that extra cosecant and cotangent. I realize that that was spelt wrong, so I will fix that. Cosecant, there we go. So that du takes care of that extra cosecant and cotangent, and this will turn into the integral of u squared times u squared minus 1 du, but of course my du had an extra negative, so I gotta be careful with that extra negative. And whether you bring it on the outside of the integral or on the inside, it doesn't matter. You're going to have to distribute it anyways. So let's do that. So this will become the integral of negative u to the 4th plus u squared du. So negative 1/5 u to the 5th plus 1/3 u cubed plus c, but my u was cosecant, so negative 1/5 cosecant to the 5th of x plus 1/3 cosecant cubed of x plus c. Ta-da! All right, you're doing good. There's a few other trig identities over here that just weren't up there on the first page, so I thought I'd just remind you of the sum and difference identities. Again, more trig identities that you probably don't see very often, but it's a good reminder. This is the ones, these trig identities you would only need if the arguments of the trig in the integrand are already different. So that's what we mean by like that a times x and that b times x. You can see that they're different. So just like this example, the sine of 5 times x times cosine of 3 times x. So in that case, if I were to use a trig identity, which I'm going to, I have a sine times cosine. It looks like that's this middle trig identity right there, where my a is 5 and my b is 3. This could be just a plug and chug. So this would become the integral of 1/2 sine of a minus b times x. So 5 minus 3 times x plus 1/2 sine of a plus b times x. So 5 plus 3, which is 8x dx. And then it's an easy integral. So then that becomes the antiderivative of sine is negative cosine. Just don't forget to divide by the constant multiple. Same thing for the other one. Don't forget to divide by the constant multiple and then simplify. So negative 1/4 cosine of 2x minus 1/16 cosine of 8x plus c. Ta-da! Awesome, awesome, awesome. All right, last little bit here for this section 3.2, which is all about trig integration, using tons of trig integrals. Here's a couple of reduction formulas. Both of these two will be given to you, so you don't have to worry about memorizing those. We just have to know how to use them. So when you see something like just a tangent or just a secant to the power of some number, you just plug and chug. Truly, really just plug and chug. So here's a tangent one. We'll just practice it. Tangent to the fourth. In that case, my n is 4. Let's write that down. My n is 4. And then you just plug it into the formula, like a very truly, literally just plug it into the formula. So this will become a 1 over 4 minus 1 times tangent to the power of 4 minus 1x minus the integral of tangent to the 4 minus 2 of x dx. And then simplify. So 1/3 tangent cubed of x minus the integral of tangent squared of x dx. The hard part is now that I have the formula, I have to still finish off the problem. So then I have to finish that integral. Remember, you keep going until you don't have an integral here. So you could use the reduction formula again. Go for it. That would be fine. This is one that I think we know, and you should have learned it in Calc 1, but if you didn't, I'll show it to you right now. It's no problem. Excuse me, tangent squared, if you look at those Pythagorean trig identities again, tangent squared is secant squared of x minus 1. Then this becomes 1/3 tangent cubed of x minus the integral of secant squared is just tangent. And then the integral of 1 is x. So then I can distribute that negative. So 1/3 tangent cubed of x minus tangent of x plus c. Ta-da! So the reduction formulas for both secant and tangent will be provided to you, but make sure you know how to use them. So definitely practice those. I would recommend try that same one using that reduction formula for secant to the fourth, or maybe secant cubed or something, and just make sure that you know how to use those formulas. All right, that's all there is for 3.2. Thanks, guys.